Picture yourself gazing out of your window when, out of nowhere, a solitary, brilliant light abruptly appears in the sky above. This dazzling celestial body shines as brilliant as the full moon on a nighttime sky, or possibly even brighter, and its radiance is discernible even in daylight. If you were able to witness this brilliant light in the sky, it could already signify a dire situation. This unexpected star has unleashed a catastrophic barrage of gamma radiation and X-rays, causing the Earth's ozone layer to disintegrate and exposing us to the perilous intensity of the sun's radiation. Additionally, hurtling towards our planet at velocities ranging from 10,000 to 40,000 kilometers per second is a cataclysmic wave of stellar matter and debris, a dying echo of an exploding star. This wave carries billions of tons of blazing material, poised to sweep across the Earth's surface like a tidal wave of flames. This scenario is akin to a supernova event, or at least one possible interpretation of what we might encounter if such an event were to happen near us. Let's kick things off with some encouraging news. Supernovae within our galaxy are relatively rare occurrences. While astronomers regularly observe hundreds of supernovae each year in galaxies beyond our own, this abundance is largely due to the vast number of galaxies scattered throughout the universe. In our Milky Way, which is much closer to home, we typically witness only about 2 to 3 supernovae in a century. This means that the chances of a supernova occurring tomorrow aren't particularly high, but they're not impossible either. According to archaeologists, Earth has likely encountered a supernova at some point in its 4.5 billion years of existence. To begin with, we reside in a region of space known as the local bubble, which is a relatively thin, populated area of interstellar space spanning about 1,000 light-years across. This region is believed to have been created by a supernova explosion that happened some 10 to 20 million years ago, a time when our planet already existed. I've discussed this in more detail in another one of my videos, which you can check out here. Scientists have also found evidence of another supernova event that occurred approximately 2.5 million years ago. This evidence is in the form of elevated levels of iron 60 and manganese 53 found in a specific layer of the geological record. Fortunately, this supernova was distant enough not to pose a threat to us. However, this may not always be the case. Some scientists theorize that the extinction of woolly mammoths around 13,000 years ago might have been triggered by a massive piece of debris from a supernova colliding with the Earth. The impact site showed magnetic spirals and contained radioactive potassium-40, a substance typically found in supernova ejecta. This evidence suggests a connection between the extinction event and the supernova. Even earlier, mammoth tusks from 34,000 years ago were discovered, featuring tiny impact craters caused by grains of slightly radioactive iron hurtling at speeds of 10,000 kilometers per second. As you might recall, this is one of the potential speeds at which supernova explosions travel. Needless to say, this would not have been a pleasant experience for the mammoths involved. An astute observer might note a critical fact, though. If life on Earth began approximately 3.7 billion years ago, and we faced 3 supernova explosions impacting us in the last 20 million years, and life is still thriving overall, it suggests that while supernovae can be destructive, their impact largely depends on proximity. When it comes to supernovae, the universe indeed provides us with a pretty large coffee table. To grasp the scale of these explosive events, it's essential to understand the forces at play, which means delving into how supernovae occur. Supernovae can originate from 2 primary paths, but in both cases, it requires the right kind of star. The case of a Type 1a supernova typically involves a white dwarf in a binary system gradually or rapidly siphoning off materials from its companion star until it reaches a critical mass. This process is not fully understood, but the basic idea is that a white dwarf, which is essentially a dense star primarily composed of carbon in a gigantic diamond-like core, reaches a delicate balance between 2 powerful opposing forces: electron degeneracy pressure and gravity. In simpler terms, atoms tend to resist being compressed too much because their electrons prefer to maintain specific distances from the atomic nucleus and resist densification beyond a certain point. However, gravity is an immensely potent force, especially in a dense mass like a white dwarf, where even a small section the size of a sugar cube can have the mass of a car. In a binary system, as the white dwarf continues absorbing matter from its companion star, gravity eventually overpowers the resistance offered by electron degeneracy pressure. This results in a catastrophic collapse, triggering carbon fusion. Within a matter of seconds, most of the star undergoes fusion, creating heavier elements and releasing an enormous amount of energy as the star settles into its slightly more efficient new configuration. The energy unleashed during a supernova event is staggering, totaling around 1/4 of a raw decillion joules, which is represented as 1 followed by 45 zeros. It's highly unlikely that you were already familiar with such a colossal number, so if you claim otherwise, it's likely not accurate. All this extraordinary energy is released in just a matter of seconds. Consequently, the star ejects its entire contents in all directions, propelling them at approximately 6% of the speed of light. This eruption results in a torrent of predominantly gamma radiation cascading throughout the galaxy. The intensity of this celestial phenomenon is astonishing, shining 5 billion times brighter than our Sun. It continues to burn brightly for a few weeks until the ejected material has traveled far enough for the overall energy level to begin dissipating. The second type of supernova, Type 2, follows a somewhat similar pattern, but instead of involving a white dwarf, it features a massive star, typically at least 5 times more massive than our Sun, nearing the end of its life. These massive stars remain ablaze due to both electron degeneracy pressure and the heat generated by fusion processes. However, just like in Type 1a supernova, a point eventually comes when this delicate balance collapses. In this case, it's because the star exhausts its nuclear fuel. Without the additional energy from fusion to counterbalance the star's immense gravitational pull, electron degeneracy pressure alone can't withstand the star's weight. The outcome is similar, with some of the massive star's material often collapsing into a neutron star or a black hole, whereas white dwarfs typically vanish entirely. Regardless of the specifics, the sheer scale of material and energy released by a supernova is mind-bogglingly vast. Understandably, anything near such an event would be subject to rapid and overwhelming destruction. The energy unleashed during a supernova is so immense that it can rip apart a star, and if a planet happens to be nearby, its chances of survival are virtually nil. Fortunately, our Sun won't go supernova due to its insufficient mass. However, in the unlikely event that it did, Earth would likely be either partially or completely vaporized, with its rocky surface reaching temperatures 15 times hotter than the Sun's surface before being dispersed over the following weeks. Interestingly, the most significant danger posed by a supernova doesn't necessarily involve vaporization. In 2011, experts from the University of Cambridge calculated that even planets situated at a distance of 15 billion kilometers from their star, roughly 100 times the Earth-Sun distance, would remain intact. Instead, they would be sent drifting into space as their star disintegrated. Nevertheless, the hypothetical ecosystem of such a planet would face unique challenges, including rapid cooling. Even if a planet's surface remains intact, it doesn't guarantee the sustainability of life. Aside from the blinding brightness of a supernova, which can outshine an entire galaxy and harm vision, the removal of the atmosphere would trigger problems. High radiation levels, even if not immediately harmful, would alter the chemical composition of the atmosphere, increasing the risk of radiation poisoning and causing mass extinctions as these events propagate through the food chain. Scientists estimate that this kill zone extends within 25 light-years. Beyond this range, the destructive potential of a supernova begins to diminish due to the vastness of space. However, it's worth noting that the potential asteroid impact that might have contributed to the extinction of mammoths originated from a supernova 250 light-years away if it indeed occurred, suggesting an element of unfortunate timing. In general, we wouldn't observe any damage from a supernova at such distances. radiation levels wouldn't be sufficiently high to cause mass extinctions. Beyond a distance of 500 light-years, the event would hardly be noticeable, except perhaps as a brighter star in the sky. This leads us to a critical question. Within 300 light-years, are there any stars with the potential to go supernova that we should be concerned about? Fortunately, scientists are reasonably confident that the answer is no. Massive stars are easily detectable, and the only two stars at risk of going supernova, Betelgeuse and Antares, are both over 400 light-years away. Detecting white dwarfs poses a more challenging task due to their diminishing brightness, making them traditionally hard to identify. However, in 2013, ESA's Gaia Space Observatory provided an abundance of data, enabling scientists to pinpoint 13,000 white dwarf stars within 326 light-years of us. Despite this significant number, scientists believe that none of these white dwarfs are on the verge of exploding anytime soon, at least not within the next few 100,000 years. Regarding Betelgeuse, some scientists speculate that this red giant might go supernova much sooner, possibly within the next few decades. This hypothesis is based on the assumption that Betelgeuse has a considerably larger radius than previously estimated. If this conjecture holds, we could potentially witness a local supernova during our lifetimes. Nevertheless, certain models suggest that even if such an event were to occur, we might not have much to worry about. The shockwave emanating from Betelgeuse would take time to reach us, and when it eventually did, it would likely possess less force than the solar wind, meaning our protective heliosphere should keep us safe. So there you have it. While supernovae are among the most massive explosions in the universe, through some fortunate stroke of luck, our corner of the galaxy has little to fear from them. The chances of us being impacted by even neighboring stars like Betelgeuse, which are slated to go supernova, are incredibly slim. Our planet indeed faces its array of cataclysms such as floods, earthquakes, and hurricanes, which can bring devastation to communities in an instant. Space remains a hazardous place as well. However, it's reassuring to know that planetary annihilation due to supernovae is probably not a concern on our list of worries. Supernovae serve as some of the most significant explosions in our universe, and they also provide a useful benchmark for measuring distances in space, thanks to the consistent luminosity of Type 1a supernovae. Scientists employ clever mathematics to calculate the distances between these celestial events and us. But why leave all the fun to the scientists? You can join in on the excitement too, thanks to the sponsor of this video, Brilliant. Brilliant offers easy and interactive online courses that have been invaluable in helping me grasp the mathematics that underpins the science discussed on my channel. They don't just teach math. Brilliant offers thousands of lessons covering science, computing, and various STEM subjects, with new content added regularly, including a chapter on supernovae as part of their astrophysics course. If you're eager to expand your understanding of the universe, or simply want to enhance your key skills, I encourage you to click the link in the description below to start your free 30-day trial with Brilliant. The first 200 of you will even receive a 20% discount on your annual subscription. Give it a go! Thanks for watching, and if you're interested in learning more about space threats, please let me know in the comments. You can also explore a great playlist that you'll likely find captivating. Finally, a big thank you to my patrons and members. And if you'd like your name added to this list, check the links below. All the best, and I'll see you next time.